Okay, for problem two, um, you are described a situation where these two projectiles are being launched with the velocity of v0 at two separate angles. The two angles kind of compare in this fashion here. Student argues the projectile fired at angle 2 will have a greater velocity at the top of its trajectory than the projectile fired at angle 1 because it will not have as big of a horizontal displacement. And then we're asked to kind of criticize the reasoning, right? Is any aspects of it incorrect? And then kind of explain our reasoning for our criticisms, right? Just to clarify the situation, right? So you have a projectile fired at angle 1, and then you have an object fired at angle 2. They both have the same the same velocity, but they have different angles, right? So this is fired at v0. This is also fired at v0, but you can see the angles are different, right? One's steeper than the other. If we follow the sort of the path of the trajectory, this one will probably make that curve like this and come back down. And then the blue one will curve higher and come back down, and then maybe come down like this, right? This possibility might go further, might not go further, really depends on the situation. But at the very top of the trajectory, we're being asked which one has a greater velocity. At least the student is trying to argue that number 2 would have a greater velocity. Well, at that point there, its velocity, and this is something you need to be clear on, is that you always have just the horizontal velocity, right? So its velocity at that point there would just be its velocity in the x direction. Whereas same is true for the other one. We'll see that its velocity is greater in the x direction than the blue one, or number 2 there, because when they're fired, right? If you look at a component like this, something's fired like this, in the x direction, right? That value is going to be greater the smaller this angle is, right? The closer this comes to the horizon or to the x direction, the more the velocity, so more of this velocity is going to be pointing in the x direction, right? And if it's steeper, then more of it will be pointing in the y direction. So the one that has a lower angle would have a greater horizontal velocity when it's launched, and then the blue one would have a smaller horizontal velocity when it's launched. Okay. What's also true at those points is that the velocity in the y direction for both is 0. That's why it reaches its highest point, is because that velocity becomes 0, and so it can't climb any higher. And so then it begins to fall towards the ground again, due to gravity, pulling it down. So at those points, the only velocity that counts is the horizontal velocity. And we already know that the one that has a smaller angle has a greater horizontal velocity. So when we're comparing the velocities at that point, at our highest point in the trajectory, the one with the smaller angle would have a greater horizontal velocity. So their reasoning, right, that it has that theta 2, first of all, is going to have a greater velocity is wrong. And then that it's due to the fact that theta 1 will not have as big of a horizontal displacement. Or sorry, theta 2 will not have as big of a horizontal displacement. First of all, displacement really is irrelevant to this problem, right? So talking about velocities, we don't really care about displacement in this situation. So it won't travel as far horizontally, great, but that doesn't really affect its velocity necessarily. So there's two things kind of to address here. One is that theta 2 will not have a greater velocity. Since its horizontal velocity is lower, and at the highest point only horizontal velocity remains. Okay, so that's the first thing to correct. And then secondly, displacement is irrelevant in this situation. All right. For part B, it says the student makes a mistake and derives this equation for the projectile's maximum height, the h max v0 squared cosine squared of theta, and then over 2g. We don't want to kind of work out derive a separate equation to correct it. We just want to look at it and kind of explain what's wrong with it. Basically, if we look back to this diagram here, if we're looking in the x direction, so the velocity in the x direction, that's going to be equal to my velocity, launch velocity times the cosine of theta, because cosine is relevant to the adjacent side of the angle, not the opposite side, right? So we're looking at Vx equals V naught cosine theta, right? That means that in this equation that we're shown here, the component of velocity that they're looking at is the horizontal component, and we don't need the horizontal component when we're talking about a vertical distance, right? We want to know how high this thing goes, and so we would only be concerned with the vertical components. So we would only be concerned with the vertical component. I know it's really hard to read this writing, but that's why I'm narrating it as well. We'd only be concerned with the vertical component, not horizontal. So we should be looking at V naught sine theta when considering the vertical distance or vertical height traveled. Okay. All right. Then we're asked to compare the magnitude of the landing velocity. Magnitude just means the size of the velocity, how big the velocity is. Doesn't matter whether it's positive or negative. And of the two projectiles fired at different angles, right? This is a little tricky because you might think, well, sort of earlier, the angle did matter when we're talking about the highest point. And that's we had to separate the x and y, right? I should mention just sort of in any parabolic motion, right? So if you have an object that's launched upwards at an angle and comes back down, they're fired at some velocity upwards at an angle, right? That velocity is lost as it goes up due to gravity, right? So over here, the velocity in the y direction is 0. It still maintains its x direction velocity, right? But it loses a lot of the y, all of its y velocity. As it comes back down, it begins to gain it back, right? So by the time it hits the same vertical position, the velocity is regained in the y direction. And so the velocity has basically changed direction. It still has the same horizontal component, but the vertical velocity is equal and in opposite direction as it was originally. So I guess just to kind of clarify a little bit more. So if there is some value to this velocity, let's say it's launched with a horizontal velocity of 3 meters per second, and then a vertical velocity of like 10 meters per second, it'll lose those 10 meters per second when it hits this point here. So over here, it would have just the 3 meters per second horizontal, no vertical velocity. And then when it comes back and it hits this point here, it'll have a negative 10 meters per second and still keep the 3 meters horizontally. Right, so it loses velocity in the vertical direction and then gains it back in the opposite direction when it comes down. So the velocities in both ends of this parabola are equal, just in opposite directions, right? One's kind of upwards, one's downwards. And this happens for any object that kind of goes through this process of going up and then down in parabolic motion. And so if they were both fired with the same initial velocity, they should both end up with the same final velocity before they hit the water. And basically that's the description. The reasoning here is that as the projectiles travel vertically, they lose and then gain back their vertical speed. So at the same vertical position, they would still have the same magnitude of velocity, right? So once they hit zero, when they land up and down, they would have the same magnitude of velocity or speed. Okay. The last part of this problem is, so they're now placed in a platform. So kind of think of it like this, right? Platform H, height like this. The first object is launched upwards, some velocity in that direction, and then the second object is launched horizontally, like this, with I don't want to clearly state whether one's greater or less, but some other velocity to the right, like this. Okay. We want to compare the vertical components of the velocity, right? So initially, the red one here, the v2, does not have vertical velocity, but it does gain it as it comes down. And so by the point it gets here, when it's about to hit the ground, right, it does have some velocity in the y direction. The blue one, it'll climb up some. It'll stop eventually because the gravity pulls it down, and then eventually it starts to come back down and then accelerate downwards like this, right? So the reason I know which one's greater here is because if we were considering, right, this trip upwards and downwards, sort of this first half of the trip, right, starts with velocity upwards and then it ends with a velocity downwards, right? So when it comes back down to the same height, h, v1 will be the same, but in the negative direction, right? And so this is effectively like you throwing down the rock instead of just throwing it upwards, right? And so you're comparing here an object that was thrown horizontally versus an object that was thrown vertically downwards, and seeing which one will hit the ground faster or with a higher speed, right? Obviously, it's going to be the one that has the initial velocity downwards. It's going to go faster. And that's basically what's happening here, is that v1 is going to have a greater velocity than v2 in the y direction, because as it climbs up and it climbs back down, that velocity that you were throwing it up with now becomes the velocity it's being thrown down with at that height, right? So at height h, when projectile 1 is coming down, it has a greater velocity than projectile 2 had at that same height. And both are accelerated by gravity. So they both speed up towards the ground, but V1 starts with an initial velocity downwards.